Good afternoon, folks. In the interest of trying to keep to time, I think we better start because we're already a bit late. This session, I believe, is called Fundamentals of Samples and the Experiment. And the first speaker is Ralf Flaig from Diamond Light Source.
Organizers, is this working? Yeah, okay. So thanks for the organizers to giving me the opportunity to talk about the data collection and processing pipelines, and I've been given this title for the 21st century. So I will make some assumptions about the 21st century. So basically, I will assume the case of an MX beamline on a third or fourth generation synchrotron source, being equipped with modern hardware, especially a fast pixel array detector. I will talk about the cryo-cooled experiment and assuming the rotation method. So I won't be able to talk about lots of other interesting developments that are going on, like room temperature serial methods, electron diffraction, or sample preparation, which indeed also plays a hugely fundamental role. So what are the goals for data collection? So in principle, it should be quite simple. We should measure all the unique reflections, potentially measure anomalous or dispersive differences depending on your experimental goal, measure enough copies of each of these reflections so that you can assess the quality of the data, how well they agree, determine symmetry, and so on and so forth. Thereby, you should try to maximize the quality of the signal that is being recorded and minimizing the radiation damage. And most importantly, of course, you should be able to achieve your experimental aim. So what kind of experimental aims can you have? So here's just a list of different kinds of experiments, ranging from native data collection for high resolution model building, molecular replacement, to some phasing experiments. And I don't have the time to go to details of each of these, but each of these experimental aims have some high priorities and some low priorities. So for instance, for the high resolution model building, you want to collect high resolution. This is not so important for molecular replacement or phasing approaches. In some cases, speed is maybe an important factor. In others, it is not. And for each of these sort of experimental aims, the beamline or instrument needs to be equipped with certain types of hardware. Yeah. So you need to be aware what is actually your question, what is your experimental aim? So I need to cover first some of the geometric strategy, and this has been already covered in the past by excellent papers from Doubted. So basically, we need to collect a complete asymmetric unit, and this is obviously means lower rotation increments for high symmetry crystals, but more measurements of reflections, as Graham already mentioned in his talk, improves the quality of the average, so using the counting statistics. And the crystal orientation can play a role. So for instance, for this point group here, depending on how the crystal is oriented, you need to either collect 30 degrees for a complete data set or 90 degrees for a complete data set. So here's just some examples of asymmetric units using the Dial's reciprocal space here. So depending on the symmetry you have, you need to collect more or less in theory. Now, always a problem if you only rotate the crystal around a single rotation axis, you will always have this blind region. And that depends, the orientation of that depends how your crystal is oriented. And the way to get around that is using two different crystal orientations. They're using, for instance, a multi-axis goniometer, and then you basically get rid of that blind region so you can collect complete data. So we're starting to now, basically our task is to fill in sort of this data collection form or table. There's lots of different parameters you need to fill in, and obviously you should also start with organizing the data, which is very important. Now, I talked about the oscillation range, and these days with fast pixel array detectors, there's not many reasons not to collect, for instance, 360 degrees of data. And if possible, as I said, collect more than one sample orientation with respect to the beam orientation for completeness, but also for statistics. Merging multiple data sets these days, as we've heard, is often automated and easy, and you benefit from some better coverage, and you really get truly independent measurements of reflections. And the cost nowadays is really quite low. It's mainly computing time and some sample preparation time. Now, there are cases still where you would probably want to collect less than 360 degrees of data. For instance, if your sample mount precludes full rotation, or if you're really pressed for speed, or if you have very radiation sensitive samples, for instance, possibly for mad experiments where you need to collect many different data sets at different energies on the same crystal ideally. So only in those cases where you would collect less than 360 degrees, then the starting angle is really still of importance. And again, I refer to papers here by Dauter. Now, in recent years, multi-axis goniometers have become more and more available on MX beamlines, and they come basically sort of in two shapes. One is sort of the SmartGon goniometer, which emulates an Euler cradle, and the other one is this mini kappa goniometer, which basically is a compact kappa geometry. And what these multi-axis goniometers do is basically they add to the main rotation axis omega. In the literature, it's often called phi, unfortunately, add different axes. Here, the chi axis in case of the SmartGon, or the kappa axis in case of the kappa goniometer. And then the phi axis would be no longer collinear with omega if there's an offset angle applied. And these multi-axis goniometers allow you to reorient the crystal. For instance, you can align the crystal with respect to the rotation axis so that you can see symmetry-related reflections on the same frame. They come with some mechanical challenges. There's always the potential for collision or shadowing. So some things that more the beamline scientists need to be aware of. There's many use cases for multi-axis goniometers. I can't go through all of them, but today I would say sort of the most common use cases is collecting complete data sets, as I mentioned, which is especially tricky for low symmetry space groups like triclinic, P1 or monoclinic data space groups. And the other one is sort of what has already been mentioned, collecting multi-sweep or multi-sweep SAT data. But basically, you use a number of different crystal orientations, maybe one which is aligned along the symmetry axis, and then some other orientations represented by these chi-phi number pairs. And this has been used successfully in the past, for instance, for sulfur SAT phasing, and I refer to these papers here. Now, luckily, Graham has already introduced the Darwin formula regarding the intensity of the expected intensity from a crystal. So I don't need to discuss a lot of details here, but one important factor is actually this I0, the incident beam intensity. And this has become could become a real problem with third and fourth generation high intensity sources where you have very small and bright beams. The other thing that I should mention is that actually also, and I think it was mentioned by Graham, that the unit cell volume also plays a role, and this omega is the rotation speed. Now, so we want to, this is where our signal comes from, basically from the sample, and your sample is so represented by these structure factor amplitudes, and the noise can come also from the sample. So for instance, the background, or if you've got multiple crystals, ice, and things like that. And it can also come from instrument errors like source instabilities, beam vibrations, cryostream problems. And in the past, especially with CCD detectors, detector noise was a problem. So people started to look at developing data collection strategy programs, like the BEST program from Popov and Burenkov, who basically try to find the best compromise for a desired resolution and signal to noise statistics to come up with best sort of data collection parameters. These days it's a different game with pixel array detectors. But what is still important, that the proper estimation of the signal and noise is fundamental for subsequent processing, something that Graham has also alluded to. So I don't want to go too much into the detector details, because again, that was covered by previous talks. But for instance, be aware of what the capacities and capabilities of the detector are. For instance, data acquisition rate. I often see something like this, and the detector could have actually gone faster So you could have used these parameters here instead of these, and you would have a data collection that would be more than 3 times faster. Something to be aware of. Here, with in the past, CCD was basically, let's say, 20th century. Now we are talking about photon counting, pixel array detectors. They don't have readout noise or dark current. They're substantially faster than these detectors. And the readout time is really in the millisecond to microsecond range, so also allowing actually interesting time-resolved studies. And these were really key to introducing the shutterless data collection modes. And usually for these kind of detectors, a single pass is sufficient. In the old days, the dynamic range for detectors was lower, so you needed often for well-diffracting crystals collect a low resolution and a high resolution path, for instance. And most commonly you'll find on beamlines Pilatus and Eiger detectors from Dectris. I can skip quickly over this because it was mentioned by Graham. You can also actually saturate these detectors. It's really hard to see. So you really need to analyze actually the pixel counts in the image viewer software. One thing that has also changed when changing from, let's say, CCD to pixel array detectors is the way the oscillation increment we are using. So in the past, with CCD detectors, you basically used what has been called often fine phi slicing in the literature. I call it wide omega slicing in the literature. Here you use basically a large oscillation increment of a degree, and you would collect full reflections and partial reflections on the same frame. But with the introduction of these pixel array detectors, basically, you can sort of slice this up and use much smaller oscillation increments, let's say 0.1 degrees, and then you get minimal overlap of reflections, and you measure much less of the background because your signal is basically the peak minus the background. So, and that is beneficial, and that has actually been proposed already in the late 90s by Flugrad, but the detector technology at that time wasn't really up for it. And then Müller has basically done some studies and found that sort of a good oscillation increment is half of the crystal mosaicity, which often comes around to 0.1 degrees. So we're filling in more of our data collection parameters here. And so still, I would recommend, at least for new projects, to do some screening, although data collection these days can be done in seconds. Traditionally, this has been done by collecting 3 images 45 degrees apart. Nowadays, we would recommend moving to more collecting a small wedge of data of 15 degrees because you get much more information out of that. And the outcome should be to determine sort of your crystal diffraction properties, what is the symmetry. It should somehow inform your data collection. Also generates these diffraction images, and you can see if there are any pathologies, how do the spots look like, and things like that. When we changed from CCD to pixel array detectors, one problem was that you couldn't see that many spots on the images because of the small oscillation increments. So, but in these image viewers, you can basically stack up, let's say, 10.1 degree images to get a 1 degree image. And then that is more sort of similar to what people used to see with CCD detectors. And the resolution you see by eye is coming closer to what the software sees. But as Graham mentioned, always rely on the software because the software actually sees more than the human eye. So we basically now can fill in the resolution. The detector distance will be adjusted accordingly, depending on energy and other parameters. And with pixel array detectors, you should still try to match detector distance to the sort of expected resolution, but it's much more forgiving than, let's say, CCD detectors, where you actually accumulated much more noise in areas where you wouldn't have actually crystal diffraction. And we assume usually on most beamlines, the detector is symmetric with respect to the beam. That means it's sort of in line, it's not vertically displaced or on a 2 theta angle or so. And in terms of resolution, again, from the Darwin equation, we know that it is limited by your sample. And there's actually an interesting study by Holton and Frankel of how small you can go basically in an optimized experimental setup, what resolution you can maximally expect it from microcrystals. And it's quite interesting read. we also need to choose the beam size. So we should match the size to avoid shooting anything that is not crystal, yeah, for instance, solvent or the sample support. So here there's some example from I-24 where they collected on some 5 by 5 by 5 micrometer cube crystals, and they used an 8 by 8 micrometer square beam in one case where they shoot crystal and a bit of the solvent around, and they adjusted beam size to crystal size. And what you can see is that basically the same I over sigma of 1.5 here is reached at much higher resolution if you pick up the beam size matching the crystal size, which is basically a reduction factor of 3 in the background. So it's quite important to have a look at this. Also, what we see more in these days, 21st century, is the availability of microfocus or sub-microfocus beams, which means that you can look at smaller and much more challenging samples, or you can select the good part of a crystal or a single crystal out of a bunch of multiple crystals. Also, one thing to be aware of is that the beam divergence in conjunction with the crystal mosaicity basically will impact on the spot shape. We will see, we call this sort of effective mosaic spread. And then the focus spot can be generated mainly using either mirror optics or compound refractive lenses. And again, those can generate a beam of different shape. And the beam shape basically or profile determines the uniformity of sample illumination. So people talk about Gaussian beam profiles like here, or top hat shape beam profiles and things like that. And you can get a different sort of flux density depending on how you generate the beam size, either by slitting down or focusing. And that is very important in terms of then when we look at radiation damage of samples. So that's another factor to be aware of. So the other parameter we need to fill in our data collection form is the energy or wavelength, the famous lambda in Bragg's law. So for native data collection, mostly use the beamline standard energy. In most cases, that's around 12 to 13 keV on a lot of beamlines, because beamlines have been optimized for these kind of setups. And for historical reasons also, because when you had selenomethionine samples, that was basically getting data around the selenium edge was also one of the reasons. Now, if you do experimental phasing, which is now done less and less because of things like AlphaFold, but still it needs to be done sometimes, then of course you need to use the element-specific energy. So you first need to look at if your anomalous scatter is present by doing a fluorescence spectrum, and then you do an experimental edge scan, basically verify the real sort of peak energies and inflection energies. Those would be 2 energies to use for collection in a MAD experiment. And then usually for MAD one, there's also high energy remote. And in some cases, people have collected also low energy wavelength. And there are other different schemes in the literature. I don't have the time to go into detail. You can also, if you have very high resolution, then you need to go to higher energies, because often the detector distance or area is actually the limiting factor. We heard yesterday also about the I-23 beamline. So in some cases, you want to actually go to very low energies, like to perform sulfur set or phosphorus set, or to do metal identification. And on the other hand, there are now advantages also of doing data collections at very high energies, but these require special detectors. For instance, work on I-24 has shown that if you use a cadmium telluride detector, if you go to high energies, there's an improvement in the mean diffracted intensity per unit dose if you go to high energy, and this has been published here. And if you use high energy and small crystals, then you could benefit potentially from photoelectron escape, as has been suggested in this paper. So now the most difficult question we get asked is, what exposure time should I use? And this is a very difficult question to ask, because it depends on so many factors. It depends on the energy, beamline, flux, other parameters, and of course it depends on the sample you put in the beam. So what we've started to do is basically, and also in other facilities, instead of setting an exposure, we recommend to setting a target dose. And the engine behind that is what we use. We use the program RADDose from the Garmin group, and it calculates a dose, but it requires sample and instrument knowledge. And here for this calculation, to start with, we assume a standard sample, so no heavy atoms, things like that. We want to improve the system by incorporating more sample information in the future. Now, if you don't have any of this instrument or sample information, then a step transmission data collection protocol would be applicable, where you start with a complete sweep of very low dose data collection, and then you basically increase the dose gradually until you find the point where radiation damage kicks in. And at some point, the crystal won't diffract any longer, and so that the term sacrificial crystal has been developed for that. So the reason why exposure time is really a difficult parameter is because if you want to have a target dose, let's say of 20 megagrays for different beamline settings that you could have, for instance, at diamond, then the total exposure varies enormously from around 1 second to more than 90 seconds. So it is really a difficult question to answer. So the question you should really ask is, what is your goal? What is your experimental aim? And what dose should I use? And again, here I just give some indications of sort of maximum dose for data set as a guide, which has been so most often used in the literature. But what you can see is there's sort of different maximum doses depending on the experimental aim. And it's usually much, much smaller for any sort of phasing attempts. But you should be aware that maximum dose doesn't mean there is no radiation damage until that value that kicks in much earlier. But it means that for some kind of aims, you could put in more dose and still get useful data out of the experiment that could still fulfill your experimental aim, whereas in other cases not possible. And the important take-home message for this is basically, if you're trying to collect everything at once, it will usually result in failure. So you need to be aware what you want to do. Also, before you hit run, really check that your sample is centered properly. I often see that things are not really quite right. So use the X-ray centering button or choose the X-ray centering options in the GUI, and also be aware of actually sample variation. So as in this example, there's like a difference in resolution of almost an angstrom, depending on where you shoot. Okay, changing gear slightly. Also, what we've introduced in other facilities now is some sort of unattended data collection. We call it UDC. And basically, we use sort of the high throughput capabilities of the beamline to come up with recipes for different experimental aims, as have been shown before. And so we use data collection based on best practice, so including some of crystallographic knowledge, basically. And so we're trying to sort of, as a target, minimizing the radiation damage for most samples. In IO4, we already use actually the dose calculations that we're going to roll that out to other beamlines. And the final data set is then ready to use for subsequent processing and so on. And this mode, as Dave mentioned yesterday, is almost exclusively used on IO3, and it's used on other beamlines, sort of interleaved with interactive uses. It is quite a successful thing. We've collected more than 130,000 samples, I think, and people are really happy with it, but it is not a replacement for remote or interactive sessions. So if you want to learn something, to speak to people, or it's not a replacement for crystallographers, and not a replacement if you want to shoot the one crystal that appeared after months, as Graham has mentioned. And so we have a mode now also more recently introduced, which is screen and collect. We collect basically this 15-degree wedge of data to get an estimate of the resolution, because that's one of the parameters we need to know. Because otherwise, if you get the resolution either by prior knowledge, some requirements you might have, or if you're very optimistic. And with the screen and collect, we basically collect the 15-degree wedge, look at the fast DP output, and then set the detector accordingly, and then collect the full data set. And we then, in the merging, we basically still use the 15-degree data. So data is not really lost. There's two modes you can use here. One is this better than mode, where samples are individual, and the other one is this and best mode, where samples are part of a group. So the way it's set up here is basically, let's say for these samples, you want to collect only the samples that have a resolution better than 2 angstrom, for instance, whereas in this case, there are 4 samples that belong to group 1, and you want to collect the best and best. In this case, you will want to collect the 2 best samples of this group. So this is the way it works. So the last couple of minutes, I just want to again switch quickly to processing pipelines and what to look at. So again, of course, it's impossible to look at all diffraction images these days with the fast speed we have, but you should still look at some, because I still see people actually collecting like 360 degrees of nice salt diffraction and so on. The other thing is on the processing pipelines, they should really answer you the question, you know, have I come closer to the experimental aim? Have I obtained the data quality that really can answer sort of my question, or is there problems in the data? So look first at sort of the summary overview, look at the dials plot, look that the crystal is actually hit by the beam. Is there consistent indexing between the different processing pipelines? And I think that was a question earlier in the session today. Look at these quality indicators that has been discussed earlier by Greta, and also look at, you know, the data completeness. This should give you already a quick overview. Then look at the triage alerts. For instance, here it has picked up there's an issue with the symmetry. Should be I2-free, but here for some reason there's an issue. In the FastDP log, mainly I would look at what other possible lattices there are, and does it make sense? And here you also get an estimate of the crystal mosaic spread. And then in the FastDP output, you see that the high resolution I over sigma still has a bit of way to go, so you can probably collect higher resolution, or you get higher resolution data by more careful processing of other packages. And then if anomalous signals is of importance, you can see that already here. In the XIA2 text file, again, you know, you can see if there's consistencies, there's a refined mosaic spreads, and also some image quality plot. Then was mentioned already in previous talks by Graham and Richard, you know, there's really a lot of information, for instance, in this XIA2 HTML file, you know, look at, for instance, correlation coefficients, completeness versus those, and other things. If things go wrong, these plots give you a very quick visual overview of what has happened. Here's a severely radiation damaged crystal. So you can see, for instance, the R values go up and the scale factor's gone crazy. I over sigma has gone down, and these radiation damage indicators, RCP and the RD plot, you can see there's some sort of, you know, increase. So it's definitely an issue there. Or are there other inconsistencies? Like, you know, there's some frames that show an issue with the I over sigma, or here there's something really, why does the scale factor, you know, decay so much? So these sort of things, something to look at. Again, Richard mentioned the reciprocal image viewing plots. So look at the completeness of the data. And what is really important is avoid systematically missing data, because that has really much more severe effect on the quality of the electron density maps than sort of randomly omitted data. I mentioned the blind regions. Also look at twinning if you have that. And we often look at the beamline when we set up doing our test crystals, look at this I over sigma asymptotic value that was also mentioned earlier. And so this gives you an indication about basically sort of, you know, am I in the right ballpark? You know, are there instrument errors? Is there crystal quality issues, and so on and so forth? So in conclusion, basically make a plan, resist the temptation to rush, even though you could collect data sets now in seconds, collect carefully. And then also look at the processing as you collect. It's quite important, because it basically tells you if you can carry on or if you need to collect more of the same project. Consider combining data. Really, multi-crystal approaches, I think, are very important and are becoming more important these days. And the question you should really ask yourself again, have I achieved my experimental aim? And always talk to your local contact before, during, and after the beam time. We're here to help. So I would like to acknowledge colleagues in my group, especially Graham, David, and Neil for discussions and slides, the whole Diamond MX group, authors of previous papers and data collection, users who challenge the beamlines and instruments with interesting samples, and the software developers. And I thank you for your attention.
Thank you, Ralf. Do we have any questions from the audience? Can I remind you, unless you want to remain anonymous, please introduce yourself when you ask your question.
Petr Kolenko, Prague, here. When I'm just thinking about a possible universal strategy for data collection, as would you recommend the users to collect the data at the maximum speed of the goniometer and as fast as possible, and then collect, let's say, 20 rotations instead of general, and then looking in scaling whether the radiation damage occurs in the 15th data set or something like this? Would this be a good strategy to treat this problem?
In terms of fast collection, there's two things to consider. Obviously, there's the limit of the detector acquisition rate, and that usually could be exploited, but we've seen some cases where it might be beneficial to collect slower. We're still exploring that. In terms of the rotation velocity, that basically depends on the quality of the rotation axis. Usually you can get quite fast. And given current detector acquisition rates, I think for a lot of modern beamlines, we're still looking are still fine in terms of the hardware configurations. I would personally always recommend, as has been mentioned before, start with low dose. Even if you don't think you see anything on the diffraction image, there's actually information there that can be processed by the software. So the criterion for me would be, is the indexing successful? And then if that's successful, you can basically, that's your sort of like, lower threshold almost, say. Probably Graham and others have comments on this, but start with a low dose data set, and then maybe you could increase or stay with low dose, and then just do multiple sweeps. Yeah, that's better than maybe still, it would still be a fast experiment. We're talking about, seconds or maybe minutes of data collection. And in the past, with CCD detectors or so, it was half an hour or longer, things like that. Radiation damage, I think, is really, if you look at the old papers, a lot has been sort of, in terms of geometric strategy and these sort of things, is all being described, and just sort of repeating that. But they mention like exposure times or crystal lifetimes of minutes or hours. This is no longer the case with third and fourth generation sources. So that's, I think, something we need to be much more aware of.
So we're already over time. It's probably poor chairmanship, but there's a question from Clemens about if radiation damage kicks in already much earlier than EG for 20 to 10 megagray. Your phone's gone off. Well, 20 to 10 megagray. All the non-phasing examples on your slides, i.e. the most common experiments done now, wouldn't it make sense to push high multiplicity from the lower priorities into the high priorities section? There's a bit more to that, but perhaps you could answer that.
Yeah. Can probably answer Kevin's offline. But yeah, basically the high multiplicity would give you a number of benefits anyway in terms of the counting statistics that I mentioned here. You get better averages. Yeah. Okay.
One quick question, and then we have to move on, I'm afraid.
Hi, Ralf. Sam Horrell, Diamond Light Source I-24.
Nice, yeah.
I don't know about you, but we are still seeing the occasional user collecting with like large phi angles, like despite the evidence you've put forward. And I don't know, what more can we do to convince them that the data does come out better and the goniometers are reliable enough to collect the data?
I think, I mean, this is obviously, yeah, meetings like this, talking to beamline scientists, but also I think with the UDC, people were, of course, skeptical in the beginning to use UDC, but now they say, oh, actually, I get quite a good result from that. And so it's sort of these sort of, we had the same discussions basically when we introduced automatic data processing. And people were skeptical in the beginning to say, oh yeah, I could process data better, but actually in most cases it's probably not the case. And now we're even time constrained. So yeah, similar discussions. But I think, yeah, if people actually realize that, okay, the sort of the knowledge and expertise that's put into these systems is beneficial, then yeah. But I still see sometimes huge oscillation increments, yeah.